There we go. All right. So let's talk about dimensionality reduction. I thought this was extremely interesting, and I learned it, of course, from the main textbook we're using here. But this is a real important issue. If you have some curve you're trying to trace out, like let me go back to a previous one just to talk about this. Like I think the first one at the bottom, we fit a sine wave kind of curve. Yeah, here you go. If you have a curve like this, how many points do you really need to trace out this curve? Now here we have something like 3,000 points. Clearly that's enough. But to trace out a curve like this, you need what? Maybe at least 10 points across this range, maybe 20, something like that. Whereas if you only had 1 point on the edge here and 1 point on the edge here, that would never be enough to describe the behavior of this. You need to have several points across this range of motion if you want to trace out that curve. And that seems obvious, but the problem is when you have high dimensionality, that becomes essentially impossible. So here we're going to count, we're going to make a hypercube that goes from 0 to 1 and has some number of dimensions, 2, 3, 10, up to 10,000 dimensions. And then we're going to take 1,000 random points in the hypercube and count how many of them are on the edge of the cube. The problem is there's a lot of edges. So if any of those dimensions is less than 0.01, then it's on an edge. So and also if it's greater than 0.99, it's on an edge, but I didn't even include those, so we're only going to find half of them with this system. But anyway, it's enough to show what in retrospect may be obvious. So the number of edge points out of 1,000 is only 25 in 2 and 3 dimensions. Most of them are in the middle. And up here, half of them are in the middle at 100 dimensions. And by the time you get up to 1,000 dimensions, all 1,000 points are on an edge. Because you have so many dimensions, of course, if you choose 1,000 random numbers, it's essentially obvious that some of them are going to be below 0.01. And what that means is you cannot remotely have enough to trace out the behavior of this. So this is a fundamental problem. And if you think about a machine learning model, learning problem like a Tesla, you have a camera pointing out the front, probably have another one pointing out the back and the side, and other cars have things like LiDAR, but at very least you have a camera pointing out the front, taking pictures at some resolution, maybe 4,000 by 4,000, and several times per second, maybe 30 frames per second. So if each pixel is an independent measurement, then you have millions of dimensions there. And from this logic, you couldn't possibly ever have enough data to train your machine learning model. No matter how much data you have, you'll never have enough data to trace out the actual behavior of it along all those millions of dimensions. But is that really what you want? That is not what your brain does. There's a famous psychological study where they tell you to watch people pass a basketball around, and while you're counting how many times they exchange the basketball, a guy in a gorilla suit rides a unicycle right through it. And most people never see the gorilla at all. Because when you're focusing on something, you pay attention to it and you ignore all the distracting other things. That's the essential thing here. You don't try to completely understand everything that's coming in. You can't even come close. You can't even understand 1% of the data that's coming in. You have to somehow pick what data is important and focus on that and ignore almost everything else. That's the only way you can possibly get anything done. And one common example I know is if somebody throws a baseball at your head, it's coming from the side of your head will jerk back within about 100 milliseconds. Very quickly, your brain decides that of all the physical inputs coming in, this is the important thing, and I know what to do about it. It's an instinct. That is, flies have the same thing. So attention is a fundamental concept here. You have to reduce the dimensionality of this, which means you have to ignore a lot of the data and somehow focus on the important stuff. Now, there's another way to look at it too. If you just consider how far apart are the samples I have, you can calculate that also. So here, I again choose a series of different dimensions, and I just choose 100 points, and I choose another random point, and I take the distance between those two, and just see what is the expected distance between points. For 2 and 3 dimensions, it's reasonable, like 0.5, but for high dimensions, it becomes a huge number, is the actual distance between points. So you don't have enough density of points to understand the behavior in this high number of dimensions. What you have to do is ignore most of it and get the dimensionality of your problem down to something reasonable, like 10 or 100. And there is a well-known way to do this called principal component analysis. So you can work with the MNIST images, which I think are the ones from handwritten censuses. Anyway, there are a bunch of handwritten numbers that have been sorted into categories. So it's a very good standard machine learning problem to analyze and develop machine vision systems. So while that's coming in, these are simple images, and I think these ones are 28 by 28 grayscale again, something on that order. And so we can use principal component analysis. And what this does is you take the variation in the images and you find out the correlation. To what extent does each of the independent variables correlate with the category of the image? So let me see if I can figure out why this is taking so long. It says it's completed. Okay, that's funny. All right, there it is. So those are what the images look like. And so now what you can do is fit a principal component analysis to it, and this will show you how many dimensions are needed to capture some of the variance. For example, if it was really just a one-dimensional bunch of data tilted at an angle in a hyperdimensional space, then there would be one all-important combined axis that you could follow that would capture all the variation, and all the other axes would just see a single dot with no variation. Basically, it's like rotating the camera around something to see how big does it look from this angle, how big does it look from that angle, how big does it look from that angle, which angles make the most variation. And after you find an angle, then you look for the next one. And so it turns out that all you need is 154 dimensions. Now, these are 28 by 28 pixel, so the original data has 784 dimensions. And as I said before, if you have an image with 784 pixels and you treat every pixel as a completely independent, equally important bit of data, that is completely stupid because our eyes don't work that way. Our eyes say, this is just a region of solid white, so it doesn't matter. The thickness of this line doesn't really matter. These regions of solid black don't really matter. All that really matters is an edge and a shape pointing in this direction, and then a shape pointing in that direction, so I can recognize a 7. So I don't take 784 numbers. I really extract 3 or 4 features from this, and that's what this will do. That's what principal component analysis do. So I said, I want to explain 95% of the variance, so we only need 150 dimensions instead of 784 dimensions. All right. And so now you can use principal component analysis. You can reduce the dimensions and then classify them with a random forest. So first I remove the extra unimportant information from the image, and then I train my machine learning model on the reduced data set, which is what your eye does. It does pre-processing to find important things like edges, and then you learn how to react to them instead of trying to correlate all the pixels at once. All right, so it's down here doing the fit. Of course, it's going to take 1,000 of those images and train on them. And it knows the shape of the image and it knows the label of the image. So this is supervised learning. And it's taking some time, but it won't take too long, just 1,000 images. And as we saw yesterday, the random forest classifier defaults to have 100 decision trees. So it's made 100 decision trees and trained them all. That's what it's doing now. All right, I'm just going to go here to look at the answer. So the answer is it chose to use 465 estimators. So it adjusted the number of trees in the forest. So it made 465 decision trees and used only 23 dimensions. And that will achieve an 85% accuracy. So remember, we started with 784 dimensions. We got it down to 23, which may seem surprising, but as you can see, humans can do it much easier. You see an edge, you see another edge. We didn't even really pick out 23 features, probably. All right. And so now you can actually see what that does. You can reconstruct the images, including only those 23 dimensions. And those dimensions are, of course, combinations of the pixels. So this is what you do. You can reduce it to 23 components, the most important 23 components, and then you can rebuild the image, including only that information. So here's the original, and there's the compressed. So you can see what it's done. This is what captures enough of the data to classify the image, to express its variation pretty well, even though it gets pretty distorted. This is the what you've done. It's a very nice way to see what dimensionality reduction is. All right, so that's the first one, an important mathematical point. Let me stop this recording.